Okay, so this is the first video that we're going to do for the proofwriting class MAT 179. And we're going to start out by talking about what's called direct proofs. And so we talk about direct proofs. The direct here means that there's no need for some fancy um, technique. So we're just going to go right into proving something. But in order to start talking about proofs, we need some minimal objects to prove things about. And since this class, our goal is to introduce you to the language of mathematics, introduce you to the writing of mathematics, and teach you a lot about that, um, we're not so focused on any particular material. So, but I need some material to work with. So we're going to start with a very basic object, but a very important object in mathematics, which is the integers. So when I say the integers, I'm going to use these curly brackets to denote sets. We're going to do a whole chapter discussing sets, but for now, I will just keep it simple and talk about the integers. And here I'm denoting the integers with this blackboard Z, which is very common in mathematics. In fact, completely universal in mathematics. And I'm just talking about all the numbers 1, 2, 3, 4, so on and so forth, that you can count 0 and all their negatives as well. This collection of numbers is called the integers. And we need some basic facts about the integers, which we're just going to take for granted in this class. So I'm going to list out some facts here. And so first of all, I'll write them out in words, and then we'll write them out in symbols. So the sum of any two integers is an integer. Perhaps not too surprising. You can play around a little bit and see that that's the case. This is not the kind of thing we're going to prove. We're just going to take this for granted. Another way of writing this, though, that we want to get used to is if I take a Z1 and a Z2, and I use this symbol to say that they are elements of the integers. So you just kind of think about it as like picking out two integers, any ones that you want. Then if you take their sum, then that's also an integer. Okay, so this is just a way of saying the same thing, but in symbols. And oftentimes in mathematics, we want to use symbols to help us express things. And so I want us to get used to translating between sentences which are purely written in words and sentences which use symbols. Okay, so we're going to take this fact for granted, and you can kind of play around and justify this for yourself if you like. But we're not going to prove that in this class. And so then we also are going to take for granted that the difference of any two integers is an integer. And again, I want to write this in symbols. So we say if Z1 and Z2, and again, I can use whatever letters I like. I'm just choosing to use Z1 and Z2 here. If Z1 and Z2 are elements of the integers, meaning that they are both integers, then when I take their difference, that is also an element of the integers. Okay, good. And then the last one that we want to just take as a fact here to use going forward is that the product of any two integers is an integer. And again, to write this in symbols, we would say that if Z1 and Z2 are integers, then Z1 times Z2 is also an integer. Okay, so in this class, so much of what we're going to want to do is it's not just about learning mathematics per se. Oftentimes, it's going to be about learning how to translate between different sentences. So in this case, between a sentence written purely in words and sentences written in symbols. This is a technique that's used throughout mathematics and something that needs to become second nature for you if you want to be successful in these higher level mathematics courses. So it's the kind of thing we want to practice in this proofwriting course as well. All right, now that we have some facts that we're just going to take for granted, I want to make a definition. Okay, so here's definition 1. So we want to define even and odd integers, something that you've probably seen before, but let's make a careful definition. So an integer n is even if it can be written in the following way, which means that it can be written as 2 times another integer for some integer k. So we say an integer n is even if it can be written as 2 times some other integer. Okay, good. And so anytime we want to play with even integers, this is sort of what the definition we have to work with. We can automatically say that it's written as 2 times something else. Okay, and so we should complete the definition by saying what it means for it to be odd. So an integer n is odd if, well, now a similar flavor, but now it can be written as 2k plus 1 for some integer. Okay. Okay, so now we have a definition of even and odd, and we have these facts that we can just use now. By the way, these facts in abstract algebra oftentimes will be said that the integers are closed under addition, meaning that if you take 2 integers and add them together, you don't get outside of the set. So that's important often in algebra. The second fact, you could say that the integers are closed under subtraction. And the third fact, you could say that the integers are closed under multiplication. So these are important facts about the integers, which are not always true for every set. But for now, I don't want to go too far into that concept necessarily. I just want to have these facts so that we can prove some things about odd and even integers. Okay. And then another fact, which I suspect will not be all that surprising to you, but I just want to make it very clear, which is the next fact is that every integer is either, so we'll call this fact 2, which is every integer is either even or odd. And I'm calling it a fact because I'm not going to prove this, though I think you are happy with this fact, I suspect. And we just need to start with some things. So the facts, these are basically the only facts I'm going to give you in this class. And then from here on out, we're going to prove everything up from there. It's a little different than what you would do in like a number theory course or abstract algebra course, where you have a particular content that you want to cover and you're going to attack that. Here, I just need to start with something to start proving things. But again, our main focus in this class is to talk about proofwriting itself. Okay. And just to play a little bit here to make sure this all makes sense, right? We know 7 is an odd integer. Most likely you're comfortable with that. But just to write it in the way in the definition, I would write it as 2 times 3 plus 1, which means here that 3 is playing the role of k in the definition, right? And similarly, if I just play around with a few other numbers, 16 is 2 times 8. So 8 is playing the role of k here. And, if I look at 100, then we're getting 2 times 50. And if I look at 23, then we're looking at 2 times 11 to get me up to 22 plus 1. Okay, and so we can see who's playing the role of k in each of these examples. Okay, so now I want to look at our first proof. So we need some statement to prove, and so the statement we're going to prove here is that the sum of two even integers is even. Okay, so this is called proposition 1, but I want to start using my shorthand. So for proposition, I'm always going to write prop. Okay, so here we have proposition 1, and it's just going to say that the sum of two even integers is even. Okay, notice this is a little bit different than what I called fact 1, which said the sum of two integers is an integer. That we're taking as a fact that we're not going to prove. But now I'm making a statement about particular types of integers, in particular even integers, right? So we're saying that the sum of any two even integers is not only an integer, but actually is even itself. Okay. Hopefully this is not too surprising of a fact, but we should play a little bit, right? So we could start with the simplest example. 2 plus 2 is both even. Of course, that's equal to 4. And the point is that I can write it as 2 times 2, right? So I have to be able to write it as 2 times some integer, in this case, 2 times 2. Okay. Let's play a little bit more. I want to get us into the habit that when you prove something, before you prove it, you should develop some intuition or understanding about the statement itself. You shouldn't just try to prove something you don't even understand yet. So this is a very simple proposition, so it's not going to take us a long time to understand what it's saying. But even so, I want us to get used to taking some time to just play. Before you try to prove something, just play a little bit. So 6 plus 10, those are both even integers. That gives me 16, and I can write 16 as 2 times 8. Let's just do 1 or 2 more here. So 20 plus 100, those are both even integers. That gives me 120, and I can write that as 2 times 60. Okay, so we see here several examples. Now for this last example, to try to get us a little bit into the idea of what we're doing with the proof, let's try to rewrite. So we know that 20 is even, so we can write it as 2 times 10. And we know that 100 is even, so we can write it as 2 times 50. So notice that both numbers have a 2 that we can pull out. So if I pull that out, I get 2 times 10 plus 50. Okay, so the point is, when we go to prove this, we're not going to have specific numbers anymore, so I can't actually add them and get anywhere. But each of the numbers is going to be even, so I can write them a certain way as 2 times a number, and then there's this sort of algebraic operation that's staring us in the face, right? So that's going to be the idea in the proof. So let's move from playing around to coming up with some more of an idea. And so oftentimes in this class, I want to get us into the rhythm of first playing around like we just did with specific examples. And then we want to just do what I might call a proof sketch, where my goal in a proof sketch is not to write things carefully. You should think about this as like a rough draft that you might write in an English class, right? My goal here is not to get everything perfectly correct, but just to get some ideas down and try to start understanding what's going on, right? So first of all, if we take n and m, which are integers, and say that they're n and m are even, then first of all, we know by definition, right? So by definition, right, that means that n can be written as 2 times k1, if you will, and m can be written as 2 times k2 for some integers k1 and k2. Okay, that's just the definition of even, right? So now I have something to work with though. So now I can go into adding them. So, okay, I want to take the sum and I want to say that it's even, right? So, well, the sum is 2k1 plus 2k2, right? And now I see that I can pull a 2 out just like we did before, but now we're doing it in general. And now the point is that what we have left over is also an integer. So now we've seen that the sum of two even integers can be written as 2 times an integer, and that's what it means to be even, right? Okay, so because we were doing a sketch, I am not being super careful. I'm not really writing out all the details, but now we see the idea, and now I want to go into writing a careful proof, okay? So I'm trying to model for you the strategy you should take in general when improving things. Sometimes when we're proving something as simple as two even integers, the sum of two even integers is even, some of this might feel a little overkill, but I want us to get in that habit. So I'm going to do it even for this um, quite simple fact. But now let's go into the proof. Okay. So first of all, now when we're writing a proof, this is like the final draft of your English essay, right? So we want to make sure we dot the I's and cross the T's, and we want to communicate to the reader in a way that we should expect them to understand. And so also, we shouldn't take for granted anything we wrote when we were playing around with numbers. We shouldn't take for granted anything we wrote when we did a proof sketch. All that was for us to understand what we were trying to do. And the reader doesn't see that, right? So now all they see is the proof. So we need to communicate anything and everything that they need to understand. Okay, so first of all, we should just give them the assumption. So assume that n and m are integers, are even. So particularly n and m are even integers. Okay, by definition, this means that n is equal to 2 times k1 and m is equal to 2 times k2, where k1 and k2 are integers. Okay, so far we're just communicating to the reader what our assumptions are and using the definition to rewrite n and m in this convenient way. Okay, so now we have to do something with that, right? And so we know what to do from our sketch. So then if we add n plus m, because that's the thing we want to try to show is even, and use our characterization of n and m, and now we can do a step of algebra, pulling out the two. Okay, great. Now we need to wrap this up for the reader. So again, since by these facts I gave you, fact one, we know that k1 plus k2 is an integer. We have shown that n plus m equals 2 times an integer, where L equals K1 plus K2. Okay, so this part, I will argue, is not necessarily needed to be in the proof, but we chose to express the fact that we can write m plus m as 2 times an integer L. We think maybe we want to express it this way because we think it'll make it clear to the reader. And now we just want to wrap things up by saying that, therefore, by definition 1, by the way, I'm going to often abbreviate these things DEF for definition. This means that n plus m is even. Done. Okay, when you end a proof in mathematics, one way to do that is by putting this little box. That just tells us that the proof is done. Okay. Another thing that people like to do is put QED, which is a Latin phrase, but I don't like to do that, so I am not ever going to do that in this class. I'm always going to end a proof with a box. But there are several other ways people like to end proofs out there. You might see it sometime. Okay, so there's our first proof. It's a short proof. It's good to start with a short proof. And before we move on, I just want to point out a little bit of structure here. So often, almost every single proof will start by naming some assumptions. So that's what the first sentence did. And then almost always after that, you'll unravel those assumptions by applying some definition or something. So that's the first thing we did. I state that n and m are integers that are even. Then we unravel that and give a characterization of evenness in terms of other integers and multiplying by 2. Then we have to do something to prove the fact that we're trying to prove, which is the sum of two even integers even. So we start adding the integers, do some algebra, and then the last part of the proof is to wrap it up and explain to the reader why this has proved what we wanted. Okay, good. So there's a general structure to this proof that will be generally true of most proofs. Okay, well, let's prove something else now to practice. All right, so here's the second proposition that we want to prove. And again, I'm going to start already by abbreviating proposition by prop. And it's very similar to the last, but this one says that the sum of two odd integers is even, not odd, right? So if you're just expecting the pattern to hold, you might say odd, but you have to be careful here. If you play around a little bit, you'll see that 3 plus 7, which are two odd numbers, is even, right? And 5 plus 17, both odd integers, is 22, which is also even. Okay. All right. So we want to prove this fact. Just to play around a little bit, if you like, with 5 plus 17, how would we write 5 as in the odd number characterization? Well, we'd write it as 2 times 2 plus 1. And then what about 17? Well, here we want to write it as 2 times 8, which is 16 plus 1. And so if we just play around with those specific numbers a little bit, notice that I can group the 2 times 2 plus 2 times 8 plus 1 plus 1 here. And so that's like 2 times 2 plus 8 plus 2. And then I can pull out the 2 one more time, and I get 2 times 10 plus 1. Sorry, I messed up. Let me erase here and write that as 2 times 10 plus 1, right? Which is the same thing as 2 times 11. So the point is that I took two odd numbers, added them together, and then I wrote it in the characteristic way of an even integer, which is 2 times another number. Okay, so that's already sort of giving us some clues as to what's going to happen in this proof. Again, maybe we feel ready already to do the proof, but I want to get us in the habit of um, always first playing around with specific numbers, then sketching out a proof without being too careful and just playing around, and then lastly writing the proof very carefully. So if we just play around, remember in a sketch, we don't have to be too um, careful about writing things clearly because we're just trying to get an idea. I know I can write N and M in this odd characterization way. So that means it's 2 times an integer plus 1. And so when I go to add them, I rewrite them in this way. And now I want to use the trick that I saw before. This is like 2k1 plus 2k2 plus 1, which is the same, sorry, plus 2. So let me fix that. And now if I pull out the 2, I get k1 plus k2 plus 1. And the point here is that this guy is an integer. So I can write it as 2 times an integer. Okay, so in the sketch, we've figured out the main idea in the proof, and so now I'm ready to write the actual proof. But when I go to write the actual proof, I have to be way more careful about communicating what's going on. Okay. Okay. So now we go into the proof, and I need to start with some assumptions, right? So assume that these integers are odd. Okay. So by definition, this means that n can be written as 2 times k1 plus 1, and m can be written as 2 times k2 plus 1, where k1 and k2 are integers. So far, we've stated our assumptions and unraveled those assumptions a little bit by applying a definition. Now we have something useful we can play with. So then, if I add m plus m and rewrite them in terms of our characterization, do a little bit of algebra. By the way that you show the algebra is, there's some choices here how we want to explain this. In fact, if you look in my notes that I post to Blackboard, you'll see I make a slightly different choice. There's nothing wrong with that. There's several different ways to communicate things, but we do want to think a little bit about what might be optimal here for communication purposes. In any case, we want to show the reader that eventually we can write things as 2 times an integer, right? And sometimes in a proof, we will show algebraic steps that maybe are things that any reader could have figured out, but we try to write it in a way that makes clear what the idea is. So sometimes we write a step for the purpose of illustrating an idea and not just because we think the reader needs to see that algebraic step for their calculation purposes. Okay, now we need to wrap this up. So by fact 1, we know that k1 plus k2 plus 1 is an integer. And so this time maybe I will not write things the way I did in the last proof. Instead, I'll just say, therefore, by definition 1, n plus m is even. Yeah, because we show that it can be written as 2 times another integer. Okay, good. So now we've seen 2 different proofs. They are quite similar to each other, but good practice. And now we want to do one more proof, which is similar, but not the same. And that will be the following. So here is proposition 3. If n is odd, then n squared is odd. Okay, here's another proposition. Well, again, let's play a little bit. So if you take 7 squared, you get 49, which is odd. And if you take 11 squared, which an odd number squared, you get 121, which is also odd. Okay, maybe we don't want to play too long this time because we're starting to get the hang of this stuff. So let's go into the proof sketch now. So we want to take an odd integer so we know it can be written this way. And in the sketch, we're just trying to get the idea of what's going to happen in the proof. So let's take that and square it, right? So what happens? But by the way, just to be clear about what we're doing here, when I say squared, I mean write this out and FOIL it out is another way of saying that, right? So we're talking about 2k times 2k plus 2k plus 2k plus 1. Okay, now we're supposed to show this is odd. So this 1 at the end is good, right? We're going to keep that 1 at the end. We're not going to do anything with that. And the rest of the stuff here needs to be written as 2 times an integer. So we need to rewrite the rest of this stuff so it looks like 2 times an integer. Okay, so well, let's see. This first term can be rewritten as 2 times 2k squared. And now we're golden, right? Because all 3 of the first terms have a 2 sitting out front, so I can pull it out. And I get 2k squared plus k plus k plus 1. And the point is that what I see sitting out front is, or what I see in the parentheses rather, is an integer. So we've written it in the characteristic form of an odd integer as 2 times an integer plus 1. Okay, so that ends the sketch because now we have the idea for the proof. And now let's go to the actual proof. Okay, so again, we need to state our assumptions. So assume the integer n is odd. Okay, by definition 1, this means that n is equal to 2k plus 1 or some k. Okay, so then we can start squaring, right? So I say n squared is equal to 2k plus 1 squared, which in this case we can start writing out as 2k times 2k. And here, perhaps we can write this down as follows. And now we just want to wrap this up. So since by fact 1, 2k squared plus k is an integer, we can conclude that n squared is odd by definition 1. Okay, and that's what we're trying to prove. So that ends the proof. And I just want to say that those are the examples that I'm going to do. And so, but there are actually several more proofs of this type in the book. So for practice, either exercise that you can do or proofs that you can look at. So for practice, there are a few more proofs of this type on page 51 of the textbook. Okay, so take a look if you want to see some more practice. And if not, then you can go to the worksheet problems and see how you do.